Hello YouTube, RJ. In our last video, we were working on converting our old micro milliamp clamp-on amp meter into a high voltage power supply, and I ran into a few snags. It didn't seem like it was regulating, if you remember. Well, it turned out that was my stupidity. I wasn't thinking about it. I had disconnected all the other circuitry from the unit, so there was no load on the power supply section. So what happened is it wouldn't regulate and give me a true voltage as I was adjusting until I put a very light load on it. And so that's why when we loaded it with a few milliamps, it dropped 10 volts. When we loaded it with a much larger load, it still was 10 volts. The truth was, if I had had just a little bit of load, just a tiny little bit of load on there to start with, it would have dropped them 10 volts already, and we would have adjusted them to get our 200 volts. And then it was regulating fine. But that doesn't take me out of the woods. In the process of thinking this over, I decided I better make sure this thing is actually capable of doing what I want to do. So what I did is I jumped on the computer, I fired up LT Spice, found some models of the tubes, and I created an LT Spice simulation of what I was working on and played with it and found some important things we need to know about that may throw a wrench into the whole work. So I'm going to jump over on the computer, pull up LT Spice, and go over what I found and what issues I ran into. But first, I wanted to show you I had went ahead and made me a new face for the meter. So here's my face. I'm pretty happy with it. I wish I had moved the word volts down a little bit. It's kind of right at the edge of the top, but it's good. It come out good. It looks good. I'm very happy. What I did was I worked in photo editing software. I took the original meter face, took a picture of it, disassembled this, took it out, took a picture, and then I put it into a photo editing software. And then I measured this face and fed that in and scaled it to make sure it was the same exact size. And then I played around and created my own scales to get them where I wanted them to be. And put my little logo on it and such. And then I printed it out to some decent paper. And then I used some stick adhesive that I use on the 3D printer called Magic Goo. You may have seen it. You put it on the bed of the printer to get your prints to stick good. I found it's pretty good for things like this. And I put a little bit on the plate, the opposite side of the plate. So the original faceplate is actually still there. Because it's symmetrical, I was able to just flip it, all the holes and everything exactly the same, put my scale on the other side, which was just showed the copper. That's all it showed. Mount it back together and end up with my own faceplate. So we've got that done. That's one step of doing this, because we needed a new scale, because this is going to it's going to be under 500 volts. If I used the one scale that was on there for 1,000 volts, we would never read like maybe a third of the scale. We would lose a lot of resolution of our meter, so I didn't want to do that. Also, there was really no good scale to use then for the 100 milliamps. So I just created my own scale. And I went ahead, and at the same time I did that, I hooked up my power supply and a resistor and my meters, and I figured out the max volt, full scale voltage, and the full scale amperage, which was marked. It was 5 milliamps, but it come out not exactly 5. It was pretty close. So I got those and I calculated out, and you'll see what I used that for. It was to create some scaling resistors to be able to use this to rescale it to the new scales for our meter. So let's jump on the computer. Let me show you what I found out with this power supply. Why we had to make some changes. We had to, crank the rudder a little bit here. So I'll pick you up on the computer. Okay, here we are on LT Spice on the computer. Here is a simulation of the power supply. We've got the main power supply source giving us 470 volts, and we've got our voltage regulation tube. We've got our air amplifier, and we've got our series regulator tube. And I found some models for the tubes. Seem to pretty well come very close to what we're seeing in the unit. Not perfect, but really close. And so I'm looking at this, and I'm playing around with values of the divider here and acting very similar to what the actual unit was doing, but it does regulate. This is our load. Actually, to make it easier, what I should have done is I should have renamed this to... So anyway, I've got a 2.5K load that'll give us around 100 milliamps at the maximum voltage. And I've got the potentiometer set to give us the max voltage at the moment. Okay, so what I want to do now is I'm going to set up and I'm going to show you, first of all, the range of voltages that we can do. I'm going to change the wiper to use a parameter here called W. And I've got, I've got it here. It's going to vary between 0 to 1 in steps of 0.1, so 10% of the potentiometer. And let's run it and see what voltages it thinks we're going to be able to see. So what's my voltage at my load? And that's pretty much on it. I'm down around 140 at the low end, if you remember. I was close to 300, not quite 280 or so. So I was pretty close to this on the real unit. And so I don't have the value I really want. I would really like to be able to turn this voltage right on down. I'd like to be able to get, closer to, my 470, maybe 400 volts would be ideal, but this circuit's not going to do it. And one of the reasons I'm not going to be able to get lower is because this circuit here is, let me clear these voltages. This voltage here is around 90 volts. That's your regulated voltage. That's the reference for the air amplifier. Because it's 90 volts, we're really not going to be able to get down. We're going to have to be a certain amount above this. So there's just no way to get the voltage down with this circuit. They didn't need that for the original intent, because remember, the voltage was 272 in the unit you were targeting. So they didn't need to get down low. So that's one issue. I just can't get the voltage range I really want out of this system. But that's not the only issue. I'm going to turn this pot back, and I'm going to put it to full voltage. And I want to show you something I wasn't thinking about. I probably should have thought about this a little better before I jumped into planning to do this the way I was planning to do it using the tubes that we have. Here's one of the things I ran into. If we go to about 100 milliamps at maximum voltage on this thing, we have to consider how much dissipation on this tube. And I just assumed the tube would be able to handle, a decent amount of dissipation. But here's what I found out. If we run this and we take a look at the dissipation of this tube, it dissipates about a little over 22 watts. Now, this isn't even at the voltage I want to be at. Think about if you go up to 400 volts, how much more this will be. We're running like 250 volts. So, I mean, this is substantially going to go up. So because of that, this tube would need to be able to handle that dissipation. Unfortunately, a 12B4, when I looked it up, is not very high. It's 5.5 watts. So there's no way we can even get close to doing what I want to do with this tube as our series regulator. We can't get the voltage swing we want with this being our reference. So we run into a number of issues here. And the thing is, remember, if we turn the voltage up and we were able to get this to go higher, you would have even higher dissipation. In fact, we can calculate that. Let me pull up a calculator here. Let's think about it a minute. That's a pretty easy thing to calculate. If we're wanting 100 milliamps, okay, and we're inputting 470 volts, our worst dissipation would be if we were taking 0 volts, or let's use 1 volt to make things clearer. So if I turn the power supply down, the higher I turn the voltage up, the less dissipation on the tube there would be, because the less of the energy, the voltage this tube would need to get rid of to give me the voltage I want here, if that makes sense. So in a linear regulator, remember, that's what we do. We actually eat up the energy we don't want to the load, voltage-wise. So at 1 volt, almost all of this 470 volts needs to be done away with this tube. So if we want to figure that out, it's easy. 470 volt input and minus what we're asking to for it to give us means it has to take care of 469 volts for me. We know that we want 100 milliamps, and we know that power in watts equals voltage times current. We can see here we could have, say, 50 watts easily if we're doing, a low voltage with a 470 volt supply. We're pulling 100 milliamps. So we need 400, we need to be on the safe side. I would say I wouldn't want to go any lower than 55 watts. Well, that's 10 times what this tube can handle. So you can see I've got a problem there. I just don't see us being able to use this to do the job. Now, as far as the rest of the circuit, the transformer, the bridge, the capacitors. Yeah, that's all great. That'll handle what we want to do. This is going to be a problem. So let me pull up another setup and show you what I came up with. Okay, this is a complete schematic of the power supply I think I'm going to build, or I actually have decided to build. And I went ahead and modeled the power supply transformer and everything, basically because I wanted the practice in creating the transformer and all that. LT Spice is tricky with transformers and things. Up to this point right here, you are looking at the old unit. This is all the old unit. You've got 120 volts coming in. You've got the transformer. You've got you've got a couple 20 microfarad capacitors. You've got 200 microfarad as in there. All of this exists currently in the system. I'm going to use the half amp fuse that exists in there as my protection for the output of the transformer to protect the transformer. I'm going to leave the fuse for the AC line in there. We're going to literally take, just as you were seeing me previously, the line coming off the capacitor, and that's going to be the beginning of the new circuit. What I'm going to do, I'm going to use a component called an LR8N is actually the full designation. It's a voltage regulator. If you're familiar with a LM317, three-leg little voltage regulator that's adjustable, this is exactly the same thing, almost to the T, but it's designed for high voltage. You can use a 317 if you put your pass transistors ahead of it to drop the voltage before it gets to it, but you got to have a lot of protection. There's a lot of gotchas with that. And so why do that? This little LR8N costs like 60 cents. It's as cheap as a 317, but it's designed to handle up to 450 volts directly on it. We're not going to pass current through this. We're going to use this to drive a set of pass transistors. So I've got tip 41s in here because LT Spice didn't have it. I'm using tip 50, and the tip 50s are going to give me quite a bit of capacity. I think they can dissipate 40 watts max. So you're talking 80 watts of capacity here. So we've got a lot of capacity. So what's going to happen is your high voltage comes in here. And just like with the 317, you've got a voltage divider here that you control the voltage into the adjustment pin. And this controls what voltage you want to see. And it looks at the voltage on this out leg and it makes adjustments to keep that voltage right where you want it. This diode here is just in case that you ever get the voltage higher on the output side than the input side for some reason. If we want to bypass and allow it to bypass this part so it doesn't damage it. That's the intention of D1. So anyway, your main voltage comes into the regulator, but it also goes through two 10 ohm resistors in parallel. And their purpose is each one feeds the transistors. And what this is doing is, if I was to not use these resistors, these two transistors would not share the power. One of them would be slightly lower resistance, and it would literally pull the majority of the current. But what we can do is the resistance of these are very, very small. So if we put a 10 ohm resistor, it's giant compared to the resistance of these, and it overwhelms it. And as soon as one of them starts trying to pull more current, the resistance across this resistor will drop the current enough that the other one will then have to pick up. And so what happens is they stair-step balancing each other all the time to make sure that they're pulling fairly equal amount of current. So that's the purpose for this. So as this adjusts to a certain voltage, these transistors will come on the moment that you have 0.6 volts less on the emitter. And so what will happen is you will adjust the voltage here. They will turn on because the voltage going out is less until this voltage on this side comes up to close to this voltage, and then they will turn off. The voltage will start dropping here. They'll turn back on. And so by doing so, all the current travels through these transistors. They're just controlled by this. Off of the base of these transistors, we're going to come down to another tip 50, and I'm using another tip 50. I could use a lot of transistors here, but I used tip 50 since that way I've only got one transistor part number. So this tip 50, his base is connected to the output voltage of these. We can control the current by the voltage difference across this resistor here. And so 6.8 ohms sets me to max out at just a few milliamps over 100 milliamps. So that sets a hard, you can't go over that. The moment you try to push more current than around 100 milliamps through here, the voltage will build up enough here to turn this base on. Current will start flowing from here, stilling the current that's turning these transistors on, and will shut them down. And so what will happen is whatever the resistance here is controls when this comes on. So the moment, if you had just this resistor, the moment you hit 100 milliamps, 104 milliamps, I think it is, this will turn on enough to take your base current away, shut them down, you're done. It'll come right back on. And so it will regulate the current. Now behind that, this sets the max, is another pot that allows you to adjust the current less than 100 milliamps. So this pot adds in series additional resistance, so you see a higher voltage drop, which creates a higher voltage here, which turns this on much quicker at a lower voltage. So, or a lower current, I should say. So this way we can set the current. If the current gets above a certain amount going through here based on what we set these resistors, it turns this transistor on. It sucks the current away from the bases of Q1, Q2. You stop outputting current. So that's what this circuit is doing here. Coming out of that, we have a set of switches. This is the load switch. If this switch is open, no high voltage goes out. So this is your high voltage load switch. This is the same switch. So what happens when you switch this, you're also switching this one. Now why do I want that? Well, because I want an indicator. And so I've got a 120 volt indicator lamp on the front. I've got a power on indicator. So when 120 volts turns on in this unit, when you throw the power switch on, you're going to get the power on lamp to come on. If the load switch gets closed, you're going to illuminate the high voltage on lamp. So that's what these switches are about. This switch up here is the same type of switch, and the purpose of it is to switch our meter. This is actually our meter right here. And what we're doing is we need a way to measure voltage, but also be able to measure current, which means I've got to switch two different circuits out off the meter. So that's what this switch does. I switch the meter, here's the meter right here. I switch the meter into two different circuits depending on whether I want voltage or current. If I want voltage, I monitor this resistor, parallel resistors right here, which are tapped into the high voltage line. It's tapped in before the load switch. Now, why did I do that? Well, because if you want to set the voltage before you put the load, turn on the high voltage, you don't want to hook it over here where you can't see the voltage till you turn it on. This way you can adjust the voltage before turning the high voltage output on. On the other hand, I can't do that with the current. I've got to have current flowing to be able to measure it. So I pick up the current over here on these parallel resistors that are in line with the output jacks. That this will only work if the load switch is on, and you switch the switch and both contacts move and connect the meter to this circuit to read the current going out. Now both of these circuits have a resistor, and then they have a trimmer potentiometer, and that's so that I can calibrate the meter precisely. I can do calculations and come real close, but put it in there and be off some. So you want a way to adjust it a little. So that's what these are. You'll notice the value here is 0.33 ohms. It's pretty low. Not much drop across this, not much dissipation. But the problem is really hard to get precisely 0.33, and any little piece of wire length or whatever will change things. So I definitely needed a pot here to adjust. So what I'm going to do is these little pot resistors, both this and this, are going to go on a little homemade circuit board that bolts on the back of the meter. And then the switch will connect to the board and switch which one goes in line. What am I missing? I guess that's pretty well it. So basically I'm going to make a semiconductor based regulator for this. Let's take a look at a couple things here. One, let's change this. I'm going to rim this statement out here, and I'll show you why. What we're going to do real quick is I'm going to kick this one back in. This one is going to step the pot like in the previous. We're going to step the pot through 10% from all the way closed all the way open, and look at what different voltages this says we'll be able to get out of this power supply setup. So if I run it and I say, okay, what's my voltages? You can see that I can get all the way from 73 volts down here, so quite a bit lower than the other one, all the way up to, let me do this, all the way to 426 volts. So it's going to give me a much better swing. And one of the nice things is, if we look at that voltage, you notice that it's pretty darn even, looks very linear through the potentiometer. So you're going to have a very linear control. I'm going to use a multi-turn pot on the voltage setting so that we can get very precise settings. I've got to get the stuff coming, get it here to do this, but this is where I'm going. One of the things I'm going to do is I'm not going to build a circuit board for this. I'm going to build a little homemade one for the meter, as I said, but the rest of it, I'm going to put some terminal blocks in there just in the style that it's built now and do point-to-point wiring and build this circuit. So I'm hoping it works as well as it looks. I've got a pretty good size anodized heat sink. I'm going to put these tip 50s on to keep them cool. We should have a pretty nice power supply when we're done. Now, this may be a couple weeks before you see any more on this because I've got Thanksgiving coming up. These videos are done ahead of time, so by the time you're seeing this, it's probably Thanksgiving's over, but Thanksgiving wasn't here when I made this video, and I've got family coming in. It's our year to host Thanksgiving, quite a few people. I'll be tied up with that. I'll have to get some parts coming, have to wait on them, got some machining to do and things before I can really show you much. So you may not see this for a couple weeks. Don't worry, it's coming back. We're going to finish this thing. There'll be other videos that I pop out on other topics between now and then. So, give me a couple weeks and I'll have an update on this. We'll show you what I've got, where I'm at, how I'm making headway, and what problems I've run into. And so, hey, I know this was a little long. Thanks for hanging out with me. Hope you enjoyed it. Hope you found it interesting. Hopefully you'll come back to see more. But most of all, I hope to see you in my next video.